Hello, everyone. Welcome to this video on learning mathematics through concept and examples. Today, we are going to work on Mastery Exercise 4 from your Intro to Statistics class. The topic of this whole video is a probability, introduction to probability. So let's begin with the first example. Example 1. The table summarizes results from 979 pedestrian deaths that were caused by automobile accidents. So here is the data. So you can see we have 63, 81, 268, 567. When you add all these accidents, that will be 979. If one of the pedestrian death is randomly selected, find the probability that the pedestrian was intoxicated or the driver was intoxicated. So if you look at this table here, we have data regarding two different things here. The first one is whether the driver is intoxicated or not during that accident. Yes, driver intoxicated. Here is the result. And no, the driver was not intoxicated. Here is the result, the number of accidents. And this side, we have the pedestrian intoxicated. Is the pedestrian who involved in the accident intoxicated or they are not intoxicated? So that is the data here. So what we are asked to do is we are asked to find the probability that the pedestrian was intoxicated. As you can see here, pedestrian was intoxicated. I'll write PI, pedestrian intoxicated, or the driver was intoxicated. The driver was intoxicated. So I can write driver intoxicated like this. And once we perform the calculation, we are asked to give the answer to 4 decimal places. So first of all, if we look at the table carefully, what we see here is the number of accidents where the driver was intoxicated. Driver, yes, is this 2, 63 and 81. 63 plus 81, 144. That means there were 144 accidents in which the driver was intoxicated. And here we have 268 and 567 accidents where the driver was not intoxicated. So if we add these two, that is 835. Meaning of that is there were 835 accidents where drivers or the driver was not intoxicated. Now, if we look the other way around, the number of accidents where the pedestrian was intoxicated, we have 63 plus 268. That will be 331. So there were 331 accidents where the pedestrian were intoxicated. And here we have 81 and 567. If we add, that is 648. So that means there were 648 accidents where pedestrians were not intoxicated. Now the question here is, let's go to the question. So here we are asked to find the probability that the pedestrian was intoxicated or the driver was intoxicated. So here we can use the addition rule because we have an or here. So if we have a probability of A or B, if you remember the formula, probability of A or B is probability of A plus probability of B minus probability of A and B. So same thing here for this one, it will be probability that the pedestrian was intoxicated, probability that pedestrian was intoxicated, plus probability that driver was intoxicated, probability that the driver was intoxicated, and then minus probability that both of them were intoxicated. Probability that pedestrian was intoxicated and the driver was intoxicated. Now let's find all these values. Probability that the pedestrian was intoxicated. So pedestrian intoxicated, yes, is here. And you can see that 331 accidents were there out of 979 where the pedestrian was intoxicated. So probability that pedestrian was intoxicated will be 331 over 979. Then plus the next one, probability that the driver was intoxicated. You can see probability for the driver intoxication. So driver intoxicated, yes, we have 144 accidents in which the driver involved was intoxicated out of 979. So the probability will be 144 over 979, and then minus probability that both pedestrian and driver intoxicated. If you look at this 63, these 63 accidents were caused when the pedestrian was intoxicated, and also you can see the driver was also intoxicated. So we have 63 accidents. So we subtract that, 63 over 979. Now, if you simplify this fraction using calculator or regular calculation, you should get 0.4208. So that is the probability that the pedestrian was intoxicated or the driver was intoxicated. So that's our first example, example 1. Let's go to example 2 and read through this. A survey of athletes at high school is conducted and the following facts are discovered. Let's see what we get. 70% of the athletes are football players. 70% of athletes are football players, as you can see there. 20% are basketball players. And then 19% of the athletes play both football and basketball. So here we can say for the first one, 70% of the athletes play football, or 70% of the athletes are football players. If you want to write as probability that the player or athlete is a football player is 0.7. That is the meaning of that. If we go to the second, 20% are basketball player. So probability that they play basketball is 0.2. And then 19% of the athletes play both. So that means probability that they play football and also basketball is 0.19. So that information is given to us. An athlete is chosen at random from the high school. What is the probability that the athlete is either a football player or basketball player? So what we want is, we want probability that they are football player or basketball player. So because we have or here, and also you can see that the intersection has the probability, we use the addition rule, which will be probability that they play football plus probability that they play basketball minus probability that they play both football and basketball. Now, if we plug in the values here, probability that they play football is 0.7. Then plus probability that they play basketball is 0.2. And then minus probability that they play both football and basketball is 0.19. So now if we simplify this, 0.7 plus 0.2, that's 0.9, minus 0.19 will be 0.71. 0.71. So probability that they play football or basketball is 0.71. So that is the end of example 2. Now let's move on to example 3. Here is example 3. Suppose 26% of people own dogs. So here you can see probability that somebody have dogs is 0.26. So we can write this as probability that someone has dog is equal to 0.26. If you pick two people at random, what is the probability that they both own dog? You can see probability that they both own dog. Meaning of that is we want to find the probability, Okay, we want to find the probability that the first person has a dog and also the second person has dog. So we want to find the probability that the first person has dog and second person has dog. So what we know is if we have probability of A and B and they are independent, the formula is probability of A times probability of B. So here in this case also, the case is independent because the probability that someone owns dog does not depend on whether the next person has a dog or not. So the formula for this one will be probability that the first one has a dog multiplied to probability that second one also have the dog. So here, probability that someone will have a dog is 0.26. So this will be 0.26 times 0.26. 0.26 times 0.26. And if we multiply these two, we can multiply using calculator here. The result will be 0.0676. That is the probability that both of them have dog, which is approximately 0.0676. Okay, that is example 3. Now it's time for example 4. Okay, let's see what we have in example 4. With one method of a procedure called acceptance sampling, let's see what is that acceptance sampling. A sample of item, okay, here we have the description for the acceptance sampling. A sample of item is randomly selected without replacement and the entire batch is accepted if every item in the sample is okay. So meaning of that is in the acceptance sampling, what you do is a sample is randomly chosen, okay? A sample of item is randomly chosen. And if everything in that sample is okay, everything will be accepted. That is the meaning. So here is the question. So that was just the idea about the acceptance sampling. And here, from here, we have the question on acceptance sampling. The ABC Electronic Company has just manufactured 1,350 rewrite series. Okay, so the number of series produced is 1,350 and 120 are defective. As you can see here, 120 are defective. So let me write that information quickly. You have defective equal to 120. So non-defective or the good ones will be equal to total 1,350 minus 120. So that will be equal to 1,230. So these are good. These are the good series. We have 1,230 good series in the batch out of the total 1,350. Now, if 3 of these series are randomly selected, okay, here we are selecting 3 series are randomly selected for testing. What is the probability that the entire batch will be accepted? For the entire batch to be accepted, according to the acceptance sampling, everything should be good. That means the first series should be good, second series should be good, and third series should be good. So here the question is, let me write here, probability that the first CD, okay, selected, second CD selected, and the third CD selected, all of them should be good independently. First is good, the second is good or not does not depend on the first. So these are independent cases. So we can write probability that the first one is good times probability that the second one is good times probability that the third one is good. Now, probability that the first is good, we have 1,230 series good, 1,230 series good out of 1,350, out of 1,350. Now, if you go to second, the first one is selected. Now, out of 1,230, when the first one is selected and found good, now we know that the remaining good number of CD will be 1,229. and one CD is already selected. We know that it's good. So the total number changes from 1350 to 1349. 1349. So that means the probability that the second one will be good will be 1229 out of 1349. Similarly, the third one, now the total number of CD is changed to 1348. Two of them are already selected good. So the probability that the first one will be 1230 out of the total. The second one is 1229 out of the remaining total. Now the next one will be 1228 out of the new total. So if we multiply these three, we get the probability that the entire batch will be selected, because for the entire batch to be selected, all of them must be good. So if we multiply this using calculator, we'll get 0.7562. So that is the probability that the entire batch will be accepted. So this was the problem on something called the acceptance sampling. Example 4 is now done. Let's move on to next example, example 5. Okay, here is example 5. Let's see what is going on here. When doing blood testing for viral infection, the procedure can be made more efficient and less expensive by combining partial samples of different blood specimens. Okay. If sample from 5 people are combined, so here what they are doing is they are combining the sample from 5 people. Okay, if sample from 5 people are combined and the mixture test negative, so 5 samples were mixed and the sample test negative, meaning of that is all 5 individuals are tested negative. Okay, all 5 individuals are tested negative. We have to find the probability of positive results. See, we are talking about negative here, and suddenly here we are talking about positive. So you know that negative and positive are complement. So once you figure out the result for negative, you can subtract from 1, then you will get the result for positive. So find the probability of a positive result for 5 samples combined into one mixture. Assume that the probability of individual blood sample testing positive for the virus is 0.03. Okay, here, probability that someone is tested positive is 0.03. So this implies probability that someone will be tested negative is 1 minus 0.03, which will be, if you subtract, 0.97. Now let's see, now what will be the probability that all of them are negative, all negative. When I say all negative, all 5 negative. So that is probability that the first one is negative, the second one is negative, third one is negative, fourth one is negative, and the fifth one is negative. So this is how we can find the probability that all of them are negative. 1, 2, 3, 4, 5. And we know that probability that someone is negative is here 0.97. 0.97. And we are multiplying 0.97. As you can see, all means first, second, third, fourth, and fifth. That's why we use multiplication, because there is and. And 0.97, 0.97, 0.97, 0.97. If we do 5 times, it is same as 0.97 raised to 5. Or that is equal to, if we do that, it will be 0.8587. So that is the probability that all of them are negative. But the question here is find the probability of a positive result. So this is negative result. Now the probability of positive result will be probability of positive result will be 1 minus all negative, 0.8587. And if we simplify that, it will be 0.1413. So that's how we can solve problem like this one. Okay, let's now solve example 6. In a large population, 70% of the people have been vaccinated. If 3 people are randomly selected, what is the probability that at least one of them has been vaccinated. Give your answer as a decimal rounded to 4 places. So what is given here is 70% of the people have been vaccinated. 70% of the people have been vaccinated. That means when you select a person randomly, probability that they will be vaccinated will be equal to 0.7. Or we can say probability that they are not vaccinated will be 30% or 0.3. If 3 people are randomly selected, so we are calculating the probability for these 3 people. Okay, 3 people are randomly selected. What is the probability that at least one of them have been vaccinated? When we say at least one, meaning of that is one or more. Okay, one or more. So here when I say one or more, when we have 3 of them, we are saying that probability that one person is vaccinated, or 2 of them are vaccinated, or all 3 of them are vaccinated. That is the meaning of one or more. So first, let's try to find the probability. So we want the probability that at least one of them is vaccinated. So for this, what we need to do is we have to find the probability, okay, probability that 3 people are not vaccinated, probability that all 3 are not vaccinated. For example, what will be that? Probability that all 3 are not vaccinated. Probability that the first one is not vaccinated is 0.3. The probability the second one is not vaccinated or vaccinated does not depend on the first one. So that will also be 0.3 to not change. And the third one is also 0.3, which is same as 0.3 cubed or 0.027. This is the probability that all 3 people are not vaccinated. But we want the probability that one or more are vaccinated, which will be the complement of this one. So this implies probability that at least one vaccinated, at least one of them have been vaccinated, at least one of them vaccinated is the complement of all of them not vaccinated. So that means complement means 1 minus 0.027, because in the complementary probability, when you add 2 of them, it should be 1. So now 1 minus 0.027 will be 0.9730. So probability that at least one of them have been vaccinated is 0.9730. So that's how we can find, or we can solve a problem like this one here. Time for example 7. Every cereal box has a gift inside, but you cannot tell from outside what the gift is. So there is a gift inside, you don't know what it is. The store manager assures you that 19 of the 55 boxes on the shelf have a secret decoder ring. So out of 55 boxes, 19 have the secret decoder ring. So meaning of that is 19 of the 55 boxes in the shelf has a secret decoder ring. That means probability that it will be the ring is 19 out of 55. That is the meaning, 19 out of 55. The other 36 boxes on the shelf have a different gift inside. So it will not be the ring, it will not be the decoder ring, instead it will be something else. If you select 2 boxes of cereal from the shelf to purchase, so you are selecting 2 boxes, what is the probability that both of them have a secret decoder ring? And we are asked to give the answer to 4 decimal places. So here we want the probability that the first one is a ring and also the second one is a ring. So because we have AND, this is the multiplication rule. So probability that the first one is a ring okay, times probability. The second box also has the secret ring, secret decoder ring. Now, so out of 55 boxes, there are 19 with the ring. So probability that the first one will have the ring inside is 19 out of 55. 19 out of 55. So once the first box is selected, now you have 54 boxes remaining. And out of those 54 boxes, 18 will have the secret decoder ring because one with the ring is already selected. So when we simplify this one using calculator, we get 0.1152. So that is the probability that both of them have the secret decoder ring. Okay, so that is a simple multiplication rule of probability in example 7. Example 8, use the following probabilities to answer the question. Give your answer as a decimal rounded to 4 places. And here they have given the information. Probability of A 0.78, probability of B 0.17, probability of A and B is 0.005. One second, this should be 0.05, right? You can see it is 0.05. So ignore this part. Okay, 0.05, there we go. Okay. And finally, here we are asked to find the probability of B given A. So that is the conditional probability. We want to find the probability of B given A. So whenever you have to find the probability like that, that is the conditional probability. So what we know is, we know probability of B given A is probability of B and A, or A and B, which is same thing, divided by the probability of this second one, that is probability of A. So this formula that I just wrote down here is the formula for conditional probability. And the reason I use conditional probability is because I'm calculating the probability of B given A. Whenever we have the condition like that, we use the formula for conditional probability. So all we need to do here is plug in the values and simplify. So probability of B and A, or A and B, which is same thing, is 0.05. 0.05 for the numerator. And then the probability of A is 0.78. 0.78. So now, if we simplify this, 0.05 divided by 0.78, that will be 0.0641. So that's how we can use the formula for the conditional probability and simplify problem like this one. So that is your example 8. Example 9. In a large population, 51% of the people have been vaccinated. If 4 people are randomly selected, what is the probability that at least one of them has been vaccinated? Give your answer as decimal rounded to 4 places. So this is just like one of the problems we did before. So here they said 51% of the people have been vaccinated. So meaning of that is remaining 40% are not vaccinated, 49% are not vaccinated. So probability that someone is vaccinated when randomly selected is 0.51, and probability that they are not vaccinated is 49%, which is 0.49. So 4 people are selected randomly. What is the probability that at least one of them have been vaccinated? And we have to give our answer to 4 decimal places. So first, let's find the probability. Here we are asked to find the probability that at least one of them have been vaccinated. So first we are going to find the probability that all of them are not vaccinated. So probability that all of them are not vaccinated is equal to probability the first person is not vaccinated is 0.49. Similarly, if you select the second one, the probability that they are not vaccinated is 0.49. When you select the third one, same probability. When you select the fourth one, same probability. So this is same as 0.49 raised to 4, or that is 0.0282. So that is the probability that all of them are not vaccinated. Now, if I want to find at least one of them have been vaccinated, it is the complement of this one. So this implies probability that at least one of them, okay, at least one of them has been vaccinated. At least one of them have been vaccinated is equal to 1 minus 0.0282. And when we subtract this, okay, we'll get 0.9718. So when one person is selected at random, I mean, when 4 people are selected at random, probability that at least one of them have been vaccinated will be 0.9718, which is 97%, which is quite high. Okay, that's number 9. Let's look at number 10. Number 10 is also similar to one of the problems we did earlier. But let's find out what is given and what we are asked to do here. Okay. Table summarizes the result from the pedestrians' death that were caused by automobile accidents. If 2 different pedestrians' deaths are randomly selected, we have to find the probability that both drivers, okay, both involved drivers that were intoxicated. So when you are selecting 2 accidents, what is the probability that both accidents were caused where the drivers were intoxicated? That means in the first accident, the driver is intoxicated, and also in the second accident, the driver is intoxicated. And here we are asked to write the answer to 4 decimal places. Okay, so first, let's try to find some fundamentals here. You can see we have a question here: driver intoxicated, yes or no? Pedestrian intoxicated, yes or no? Now, if we add these two, 49 and 62, you'll get 311. And you need to know what is this. There are 311 accidents in which the pedestrian involved were intoxicated, yes. And here, if we add these two, it will be 673. So that means there are 673 accidents in which the pedestrian involved were not intoxicated. Similarly, if we add these two, 49 and 71, that is 120. Okay, that is 120. And meaning of that is, okay, 120. And meaning of that is there are 120 accidents in which the driver was intoxicated. And if we add these two, it will be 864. And meaning of that is there were 864 accidents in which the driver involved was not intoxicated. Now here, if we want to know the total number of accidents, okay, total number of accidents, that should be equal to 49 plus 71 plus 262 plus 602, which will be equal to 984. So if we add these 4 numbers here, it will be 984. Or if we add these 2 numbers or these 2 numbers, you'll also get 984. Now let's go to the main part of the question. So here what we want is, we want the probability that the first driver is intoxicated and the second driver is also intoxicated. Because we have and, this is the multiplication rule. So probability that the first driver is intoxicated times the probability that the second driver is intoxicated. And you can see driver intoxicated. If you look at this one, driver intoxicated, yes, you can see there are 120 cases. So when you select the first accident, you have 120 out of 984. The probability that the first driver will be intoxicated is 120 out of 984 multiplied to. Now, when the first one is selected, the remaining number of accidents will be 983. And out of 120 accidents, one accident is already selected where the driver is intoxicated. So 120 accidents were there where driver was intoxicated. One of them is already selected. So the remaining will be 119. 119. So now, if we simplify this using calculator, you should get 0.0148. So that is the probability in which the both driver involved were intoxicated. So in this type of problem, you really need to read through the problems. What is actually asked here, that's what you should be looking for. Here, you can see, find the probability that both involved drivers were intoxicated. That is, two accidents were selected. The first driver is intoxicated, and also the second driver is intoxicated. So you have to be very careful in solving problem like this. Read through the problem and calculate exactly what is asked there. So there are several problems with the table like this in the mastery exercise, but they are not the same, they are different. So you really need to scan through it properly, understand the problem first, then only approach the problem. Let's do one more problem involving table like this one. Here is that. Okay. Table summarizes the result from 986 pedestrian deaths that were caused by automobile accidents. So when you add all these, it is 986 in this one. If one of the pedestrian death is randomly selected, so here we are just selecting one, we have to find the probability that both pedestrian and driver were intoxicated. Okay, so this is what is going on here. We have to find the probability in which we are just looking for one random accident here. If one pedestrian death is randomly selected, find the probability that both pedestrian and driver intoxicated. Pedestrian intoxicated and driver intoxicated. If you look at the table, you can see, okay, see, driver intoxicated, yes. Pedestrian intoxicated, yes. We have 56 cases. So there are 56 cases in which the driver is intoxicated and also the pedestrian is intoxicated. And this is out of 986. So that means the probability is quite simple here. This is equal to 56 out of 986, which will be simply equal to 0.0568. So you can see, as I was telling you before, when you see table like this, it doesn't mean that the questions are always the same. The question will be different. You really need to read through the problem, try to understand what is exactly asked, and try to answer that one only. In this one, they were just asking us to find the probability when one pedestrian death is randomly selected. So it was just the one. But in this one, we are talking about two accidents. You can see that's why we look for the first accident where driver intoxicated, second accident where driver intoxicated. So you really need to read through the problem, understand what is exactly asked, use the correct formula, and then calculate your probability. So that will definitely help you. Okay, let's continue to number 12. A survey of athletes at high school is conducted and following facts are discovered. 43% of athletes are football players. 34% are basketball players. And 23% of the athletes play both football and basketball. An athlete is chosen at random from the high school. What is the probability that the athlete is either a football player or a basketball player? Give your answer as percentage. Okay, so we have a couple of information given here. The first one is 43% of the athletes are football players. So we can say probability that an athlete is a football player is 0.43. Similarly, 34% of the athletes are basketball player. That means probability that a randomly selected athlete is a basketball player is 0.34. And similarly, 23% of the athletes play both football and basketball. That means probability that an athletes play football and also basketball is 0.23. So this is given to us. Now the question is, if an athlete is chosen at random from high school, what is the probability? As you can see here, what is the probability that the athlete is either a football player or a basketball player? So now what we want is, we want the probability that the athlete chosen is either a football player or a basketball player. So because we have or, this is the addition rule, and our formula is probability that an athlete is a football player plus probability that athlete is a basketball player minus probability that they are both football player and basketball player. We have all these values. Probability that an athlete is football player is 0.43. Probability that they play basketball is 0.34. Then minus probability that play both football and basketball is 0.23. And if we simplify this one, that would be equal to 0.54. But if we look at the last part of the question here, give your answer as percentage. So if you want to change this to percentage, that will be 54%, which is same as 54%. So 54% of the athlete play either football or basketball. That is example 12. Example 13. Pollsters are concerned about declining level of cooperation among person contracted in the survey. A pollster contracts 105 people in 18 to 21 age bracket. So you can see in this age bracket, 18 to 21 age bracket, they contract 105 people and found that 89 of them respond to the survey and 16 refuse to respond. 16 refuse to respond. Okay, 16 refuse to respond, whereas 89 of them, they respond. Similarly, you can see here, when 260 people in this age bracket are contracted, 226 of them responded and 34 of them refused to respond. Assume that 1 in 365 people, 365 because here we have 105 people in that age group and 260 people in this age group, so total will be 365. Assume that 1 out of 365 people is randomly selected, or in other words, meaning of that is, if a person is selected randomly, we have to find the probability of getting someone in the age group 22 to 29 bracket, or someone who respond. And we are asked to give the answer as percentage. So let's quickly make a table here so that it's easy for us to understand the information. So we have the age group 18 to 21, and then 22 to 29. That's our age group here. And also responded or not responded. That's what we'll look here. And if we try to complete this table, let's see what we get first. Okay, if we try to complete this table, they said that in this age group, 89 of them responded, 89, and 16 refused. And in the second group, you can see 226 of them responded and 34 of them refused. And if we find the total here, if we add these two, it will be 105. Meaning of that is there are 105 people in the first group, as it is said here. And if we add these two, it will be 260. We have 260 people in this age group. The number of people who don't respond, we add these two, that will be 50. The number of people who responded, if we add these two, that will be 315. 315 people responded. So we have all the information here. Now what we have to do is we have to find the probability here. Find the probability. Now we need to find the probability. Okay, probability of getting someone in the age group 22 to 29. So what is the probability that someone is from this age group, 22 to 29 age group, or as you can see there, or who respond, or someone who responded. We can write R for them. So you can see, because we have or here, we can use the addition rule. So if you remember the addition rule for probability of A or B will be probability of A plus probability of B minus probability of A and B. So we can write the formula in the same way. So probability of the first one, 22 to 29, plus probability of the second, the probability that someone responded, minus probability that someone is in the age group 22 to 29 and they also responded. So probability that someone is in this age group is 260 out of the total. So 260 out of 365. 260 out of 365. Then plus probability that someone responded. You can see 315 people responded. So that is 315 out of 365. And then we have a minus, this minus sign. Probability that someone is in this age group and responded. So in this group responded 226. So 226 out of 365. Now we can simplify this using calculator and we'll get 0.9562. But the question says give answer as a percentage rounded to one decimal place. So this will be 95.6%, which is same as 95.6%. Okay, there we go. So that is the probability that someone is from this age group and responded. That is example 13. Quite a long problem, but if we make a table like this, it's also called the contingency table. It's quite easy to understand the problem and solve it. Example 14. A quick quiz consists of multiple choice question with 3 possible answers. Okay, so in the quiz, what we have is we have a multiple choice question with 3 possible answers. So that's like the first question, maybe that's question part A, followed by a multiple choice question with 5 possible answers. So the second problem is also a multiple choice question with 5 possible answers. If both questions are answered with random guess, so for example, if we need to guess the correct answer for the first one, there are 3 possible answers, so one of them will be correct. So the probability that they will make the first one correct will be 1 out of 3. Similarly, in the second one, there are 5 possible answers, so the correct option will be 1 out of 5. Probability of getting the correct answer is 1 out of 5. If both questions are answered with random guess, we have to find the probability that both are correct. So what we want is, we want the probability that both are correct, that is first correct and second one is also correct. Because we have and, this is multiplication, so this is equal to probability that they get the first one correct times probability that they get the second one correct. And what we know is probability that they make the first one correct, we have seen here, it's 1/3. Multiply to probability that they will get the second one correct is 1/5. Which is same as if we multiply 1 out of 15, okay, 1 out of 15 or 0.0667. And we are asked to give the answer as a percent rounded to 2 decimal places. So if we try to change these to the percentage, we multiply this by 100. So this will be 6.67%. 6.67%. So that is the probability that they will get both answers correct. So by guessing, there are very less chances that you will get both of them correct. It's just like a 6.67% only. Okay, that was number 14. Let's move on to number 15. A dice is rolled 3 times. So if you think of dice, the possible outcome or sample space for that, let me write. Sample space while rolling a dice is 1, 2, 3, 4, 5, and 6. That is the sample space. Okay, what is the probability of showing 3 on every pole? So now what we want is, we want probability of getting all 3, I mean all 6 in 3 times. That means we are looking for probability of getting 6, probability of getting 6 the first time, probability of getting 6 the second time, and also getting probability of 6 the third time. And each time you roll the die, the probability of getting 6 is 1 out of 6. So it is 1 out of 6 times 1 out of 6 times 1 out of 6, which is equal to 1/6 cube. Or if you simplify that, it will be 0.0046. So probability of getting 6 all 3 times will be 0.0046. Number 16. Valerie buys a bag of cookie that contain 9 chocolate chip cookies, 9 peanut butter cookie, 9 sugar cookie, and 8 oatmeal raisin cookies. So you can see 9 chocolate chip cookies, 9 peanut butter cookies, 9 sugar cookies, and 8 oatmeal raisin cookies. So if we look for the total number here, let's add them. Okay, total number of cookies is equal to 9 plus 9 plus 9 plus 8, which is 35. Now the question is, what is the probability that Valerie randomly selects an oatmeal raisin cookie? Probability that she selects oatmeal raisin cookie from the bag eats it. So she's eating that first cookie, and then select oatmeal raisin cookie again. So oatmeal raisin and oatmeal raisin. So this will be, and so multiplication rule, probability of getting the first one, oatmeal raisin, times probability of getting the second one, oatmeal raisin. You can see there are 8 oatmeal raisin cookie out of 35. So probability of getting the first one, oatmeal raisin cookie, will be 8 out of 35. 8 out of 35 times, once you eat one of them, now the total number remaining will be 34, and the total number of oatmeal raisin cookie remaining will be 7 only. So the probability of getting the second one as an oatmeal raisin cookie will be 7 out of 34. Now we can multiply this using calculator and simplify, and your result will be 0.0471. Seventeen. A hacker is trying to guess someone's password. Okay. The hacker knows somehow that the password is 4-digit long. So it consists of number and is 4-digit long. So password may be something like that, like this. Let's see. Password may be the first digit, second digit, third digit, fourth digit. I'm just specifying them as x1, x2, x3, x4. And each digit could be a number between 0 and 4. And these values like x1, x2, x3, x4 that I've written here, these are the numbers between 0 and 4. So 1, 0, 1, 2, 3, 4. They know this. So that means you can see the probability that they will get the first one correct is 1 out of these many. 1 out of 1, 2, 3, 4, 5. So it is going to be 1/5 for each of these. So meaning of that is, now probability that they know the password, which is they know x1, x2, x3, x4, will be probability of getting x1 times probability of getting x2 times probability of getting x3 times probability of getting x4, because the hacker must know the first one, the second one, third one, and the fourth one, because there is and, it is all multiplication. And the probability of getting the first one correct, you can see this one is one of these. So it is 1/5, 1 out of 5. One possibility out of these 5 choices, 1, 2, 3, 4, 5. So same for the second, same for the third, same for the fourth, which is same as 1/5 raised to 4, or 0.0016. But the question says, give your answer as decimal rounded to 6 places. Okay, 1, 2, 3, 4. I have only up to 4. To make 6, I can add 2 zeros there. So that is the probability that they can hack your password once they know that your password consists of numbers from 0 through 4. So there are chances that it can be hacked. Okay, time for number 18 now. Look like a long question, but may not be that difficult. Okay, a special deck of cards. Remember, this is not the standard deck of 52 cards. Okay, this is a special deck of cards that has 9 green cards, 12 blue cards, and 5 red cards. So you can see if you try to add these 3 cards, okay, 9 plus 12, which is 21, plus 5 is 26. So total 26 cards. So there are 26 cards, and it consists of 3 different colors: green, blue, and red. What is, okay, when a card is picked, the color is recorded. So they are picking up the card and they record the color. Like they pull the card and they see which color is that. Is it a green, blue, or red? An experiment, now see what is the experiment. An experiment consists of picking a card. Okay, in the experiment, what they're doing is consists of first picking a card and then tossing a coin. So you can see, picking a card, they are picking one card out of 26. Okay, sample size is 26 here. Sample size 26. And similarly, tossing coin, sample size is 2. Sample size 2, because you will get either head or tail. Now, the first part is, how many elements are in the sample space for this experiment? So you can see, while picking a card, we have a 26. And while tossing a coin, we have a 2. So that will be equal to 26 times 2, or 52. That means the total possibility or total number in the sample space would be 52. So that is the first one. Okay. Now let's look at B. So in B, let A be the event that the green card is picked up. Okay. So in this one, the event A, okay, this one is event A. Let A be the event. A be the event that green card is picked. Green card is picked first. Green card is picked first, followed by landing a head on the coin. Okay, followed by landing head on the coin. Find PA. We have to find the probability of getting A, and we have to write the answer to 4 decimal places. So it is probability of getting green on the card, and then landing on head. So this is like this one, okay, this event getting green and landing that, and they are independent, and it's and, so we multiply. So probability of getting green here, you can see green is 9 out of 26. So that is 9 out of 26 multiplied to probability of landing on head, it's half, because you have one head out of 2. And if you simplify this, 9 over 26 and 1 over 2, if you multiply that, that will be 0.1731. 0.1731. That is the probability of getting the green card followed by landing on the head. That is event A. Now in part B, let B be the event. Okay, here is B. B be the event, just like in A. Like here, we are also defining the event B. Okay, and in event B, what's going on is, let B be the event that or red or blue is picked. See, if you look at the card, we are talking about red or blue, not green card. Okay, this time red or blue is picked, followed by landing head on the coin. Followed by landing a head on the coin. Okay, followed by landing head on the coin. Now the question here is, are the event A and B mutually exclusive? Okay, so you can see that in event A, you will get the color that you are getting is green. But here in event B, you are not getting the red or blue color. Meaning of that is, these two events are exclusive. Okay, they are mutually exclusive. They don't include the same color. So A and B are mutually exclusive. A and B are mutually exclusive. Mutually exclusive. Now let's look at C. It's also similar. Let's see, part D here, event is C. So let's C be the event. Okay, there's another event. C be the event that green or blue is picked. You can see if you want to match with this one, there is a blue matching there. And if you try to compare with the first one, green is matching there. So that means this coincides with C and also with a B part. That is, this one, event C contains event A and also event B. Okay, followed by landing head on the coin. So second part is pretty much the same, landing head on the coin. And the question is, are the events A and C exclusive? When you look at A and C, you can see there is a green, there's also green. So if the green card appears here, green card may appear here also. That means, in fact, A and C are not mutually exclusive. So we can say A and C are not mutually exclusive. A and C are not mutually exclusive. Okay, that is your number 18. Number 19. Let's see what is here. A and B are independent event. So if you remember, for independent event, this is what we know. For independent events, what we know is probability of A and B is equal to probability of A times probability of B. That's what we know about the independent events. Okay, use the following probabilities to answer the question and round to 4 decimal places. So they have given probability of A is 0.14. So this one is given. Probability of A is 0.14. Okay. Probability of A and B, this one, probability of A and B is 0.11, 0.11. And probability of B is not given. We are asked to find probability of B. We want to find this probability of B. Now you can see if we want to find probability of B by itself, here we are multiplying by 0.14. So let's divide on both sides by that. So we divide here by 0.14 and also on this side by 0.14. So what we get here is 0.11 divided by 0.14 is 0.7857 is equal to, on the right hand side, these two get cancelled and you are left with probability of B. Probability of B. So we get probability of B equal to 0.7857. So that's what we are asked to find, probability of B, and we got that. So that is my answer. Probability of B is 0.7857. Now, one more to go. Here is that, number 20, the last question from your mastery exercise. So here what they are saying is J and K are independent events. So what we already know is if J and K are independent, J and K are independent, just like in the previous example, we can write this multiplication rule for J and K. So probability of J and K is equal to probability of J times probability of K. Also, you can see here we have the conditional probability. So also what we know is for the conditional probability, probability of J given K is equal to probability of J and K divided by probability of K. So this is from the conditional probability. So here is one fraction. We can also write probability of J given K as a fraction like this, so that we can simplify using cross multiplication. So what I mean by that is I can multiply 1 times that will be probability of J and K is equal to, and if we multiply this side, that will be probability of J given K multiplied to probability of K. Probability of J given K multiplied to probability of K. So now what you can do here is at this step, you can compare this equation, which is equation 1 there and equation 2 here. You can see that these are similar. On the left hand side, we have the same thing, exact same thing, probability of J and K, probability of J and K. On the right, here we have probability of K multiplied to probability of J. Here we have probability of K multiplied to this one. So these two are equal. These two on the left hand side are also equal. That means these two quantities must be same. So we can write from equations 1 and 2, Okay, from equation 1 and 2, we can say this part and this part are equal. That is, probability of J given K is equal to probability of J. So that means probability of J given K and probability of J are equal. That means the probability of J is also 0.96. So this implies probability of J is also, you can see probability of J is probability of J given K, which is 0.96. 0.96. Okay, so that's how we can solve Mastery Exercise 4. It's quite a long exercise with a lot of problems, but I hope this video will be very, very helpful for you. I hope you enjoyed this. And yeah, as always, thank you so much for watching.